So, in this class we will conclude our discussion on the special theory of relativity. We have reconciled with the constancy of the speed of light in all inertial frames of references. We have accepted that the laws of physics are the same in every inertial frame of reference as we expect them to be. We have accepted the consequence which manifests itself in terms of time dilation and length contraction, and the important thing that I would like to emphasize over here, that whenever you talk about distance, time and measures for this, measure is some unit in which you measure it. You must use your own measure, that if you are doing this analysis from the point of view of a certain observer, an observer, let us say whether it is Sita or Geeta or Jayalalitha or whoever, it does not matter. When using Sita's perspective, use Sita's measures, her distance scale, her time scale, the division of her distance by her time will give you the velocity in her frame of reference, and if you want to relate it to that of any other observer, then the transformations must be done through the Lorentz transformations. So, if you just keep track of these simple things, special theory of relativity is no longer a mystery, and one really need not be perturbed by all these discussions that one finds in some books or sometimes even more so on the internet. They make it sound as if there is some magic going on and there are only 3.5 persons who could solve this, and that kind of thing. So, you do not have to worry about those things, just use the correct measures in the correct time scales. We will conclude this discussion. We are absolutely not going to get into the general theory of relativity or anything like that, but we will sum up some of the other consequences. This has been a very fascinating field in physics. It has made important contributions to the developments in physics. Some of the famous names in the theory of relativity are Lorentz, Michelson, Einstein, and they are all Nobel laureates amongst many others. Although they did not specifically get Nobel Prize for the work they did in the context of the theory of relativity, it does not matter, but they have done not just one piece of work, but much else, and it has really revolutionized physics. What is the upshot? That we do not anymore talk about space and time as distinct entities. Space and time together constitute the 4-dimensional Minkowski space. X prime is a mix of x and t. T prime is a mix of t and x. So, there is a scrambling that is going on. So, just as a certain arrow has got components along, let us say x axis and a y axis and a z axis and so on, we now talk about events which have got components in 4 dimensions, not just 3. It does not automatically mean that the extension from the 3-dimensional world to the 4-dimensional world is of the same kind as the extension from 1-dimensional world to 2-dimensional world. or from 2-dimensional to 3-dimensional. You can do geometry on this plane in a 2-dimensional space and you add the third component, right, and you can extend your algebra, your geometry Ex Ey basis goes to Ex Ey Ez, and then you can develop your algebra and geometry by a straightforward extension. The extension to this 4th dimension is a little messy, but I will not be able to go into those details over here. But it is quite clear from this discussion here that space and time are mixed, and we must talk about events described by not x, y, z alone, but by x, y, z and t. So, there is a time-like component. So, there is a 4th component which is called as the time-like component, if you like, and you talk about events. What is space for one observer is a mix of space and time for another. Okay? What is time for one observer is a mix of time and space for a different observer. Okay? So, what you call as space is what I might call as a combination of space and time, and vice versa, depending on our relative state of motion. This has got very interesting consequences. Think of static charges. You have got a certain charge, so many coulombs or whatever. A static charge produces an electric field, right? We are comfortable with this idea. If you have a charge in motion, you have a current, and a charge in motion generates a magnetic field, right, this right hand thumb rule and all this thing. We are comfortable with that idea also. But now what is a static charge, which is a charge at rest for one observer, could be a charge in motion for another, right. So, the consequence of this is that if static charges produce electric fields and currents produce magnetic fields, what is electric field for one observer can be a combination of electric and magnetic field for another, because what one observer sees as a static charge, the other observer can see it as a charge in motion. Okay? So, what is electric field for one observer? For me it may be a purely electric field, but if you are moving relative to me, you might see it as a combination of electric field and a magnetic field. So, electrodynamics is intimately related to the special theory of relativity. Okay? It is inseparable. These are the equations of transformations. What is an electric field for one observer? Ex, Ey and Ez. This is the electric field for one observer, and if the second observer is moving with respect to the first observer at a certain velocity, he will see it as a combination of electric field and a magnetic field. So, here is a superposition of the yth component of the electric field with the z component of the magnetic field. I am not going to go into these details, but let me get this idea across to you. Okay? I will get into some of these applications when we discuss electrodynamics in one of the later units. Okay? And at that point of time we will illustrate these relations, we will spend more time discussing this. But at this point I just want to point out to you that what is an electric field for one observer is a combination of electric and magnetic field for another observer, and the transformation from Ex, Ey and Ez and Bx, By and Bz to two new fields E prime and B prime is done according to these transformation equations which I have assembled over here. They have a certain resemblance to the Lorentz transformations which transform space and time and mix them up. These are transformations for electromagnetic field, and they show up as combinations, superpositions of electric and magnetic fields, but we will illustrate this when we have a unit on electrodynamics alone, okay. Because Maxwell's equations need to be discussed in terms of the divergence and curl of electric and magnetic fields, and we have not even introduced the idea of divergence of a vector, the curl of a vector in this course. So, that is what I am going to do in the next unit. So, the Faraday lens experiment that we discussed when we introduced this topic of relativity now really makes sense. Remind yourself that when you had a magnetic field and you have a circuit which is placed in this magnetic field and you drag the field itself, and the Lorentz force itself is 0 because there is no velocity imparted to any charge in the circuit. But we found that there is a current, just as one would get if the magnetic field is held steady and the electrical circuit is dragged. And we also saw that if you move neither but just change the magnitude of the magnetic field, even then we found that there is a current. So, this Faraday lens experiment which goes into Maxwell's equations, it really makes perfect sense once you understand that space time continuum is what we must use to do this analysis, and you cannot separate space from time and then still expect electrodynamics to work. So, electrodynamics and the special theory of relativity go hand in hand, and as I mentioned when we introduced the subject, that perhaps this more than the measurements of Michelson and Morley were the motivation for Einstein to ponder over these issues, and finally he came up with brilliant answers. This particular transformation between electric and magnetic field is very well illustrated in this paper which you can look up. It is a nice it's a nice software which is developed by two of my students, Satish Kumar and Venkatesh, and subsequently they this software package was improvised by Chaitanya and Chaitanya Das and Srinivas Murthy, and it is available at this reference in Resonance. It is also there at my website, you can look it up. And when we discuss electrodynamics, we will actually run this package. Jobin, we can do that, right? Means, so we will set it up on this laptop and we can run it, but we will do it as when we discuss electrodynamics, not at this stage. And it really shows how these electromagnetic fields transform from one frame of reference to the other frame of reference, and how the observations make perfect sense, and the analysis of the implications of the Lorentz force, whatever acceleration it is to impart, will turn out, the physics will turn out to be the same in both the frames of references, because what is electric field for one observer is a combination of electric and magnetic field for the other. Now, there are other implications of the special theory of relativity, and I will again, this is in this class I am only going to sum up some of the essential consequences, but not go into any great details. Let us ask this question: what is an invariant interval? Means if you look at the length interval between this and this, we have already agreed that this length interval between this tip to that tip cannot mean the same to every observer regardless of their states, relative states of motion, right. So, if you now talk about velocity, which is a ratio of distance over time, neither the distance nor the time means the same to all observers. These do not have absolute meanings, they have got meanings in their own frames of reference, because each observer has his own measure of the length scale and he has his own measure of the time scale, and he must use his own time and his own length to subsequently do this analysis of the ratios which give velocities, subsequent ratios with another time with which will give him acceleration, and then do dynamics. Okay. So, the invariant is not delta r, it is not delta t, and to come up with the invariant quantities in the 4-dimensional space. So, we are not expecting invariants in 3-dimensional space anymore, because the 3-dimensional space does not have an identity which can be separated from the 4-dimensional world. Okay. So, the invariants of the 4-dimensional world will have some mixed attributes, and this is where we end up introducing what is called as the proper velocity. Okay. Velocity is dr by dt. We define what we call as a proper velocity, which is some sort of a hybrid quantity. This is dr by d tau. Okay. And actually, if you just look at the expression at the right extreme of this equation, it is gamma times velocity. You know what this gamma is, this square root of 1 minus v square by c square. So, this eta, which is gamma times v, is what is introduced as the proper velocity. The vector v has got 3 components. So, the vector eta will also have 3 components, because it is only that each component is scaled by the factor gamma, but we must look for a velocity which has got 4 components. So, gamma v, which we have now defined as eta, gives you 3 out of those 4 components. There is an additional component which is gamma c. Okay. So, gamma c together with gamma v is what gives you the 4 components of what is called as a 4 velocity. Okay. So, this has to be introduced in the theory of relativity. This is very often expressed by using contravariant and covariant notations. I am not going to get into this analysis and use this notation. I will probably use some of it when we discuss electrodynamics in a later unit, but not now. At this juncture, I just want to point out that you must introduce the 4 velocity, which is gamma c and gamma v, the 3 components sitting in gamma v, and this is the 4th component. And the reason to do this is that if you take the metric, okay, like the scalar product kind of thing. So, I will not go into a detailed definition in terms of the covariant and contravariant labels and how to do the contraction and so on, but you can see that these 3 components look somewhat like the v dot v scalar, right. The scalar product of a vector with itself, a dot a, is ax square plus ay square plus az square, right. So, it is ax plus ay plus az. To this we must add the eta 0, and if you construct this addition gives you c square regardless of anything else. And this is a manifestly invariant quantity, because the speed of light is a constant in every inertial frame of reference, therefore, its square is also a constant. So, you get invariant quantities from this 4 component velocity, not from the 3 component velocity. Okay. So, this is the implication, this comes as an upshot of the special theory of relativity, that velocity has to be defined in terms of these 4 components. This is and these with these 4 components, the it gives you the correct invariant quantity, which is c square. What about momentum? Momentum is what we normally define as mass times velocity, and if velocity has been, our perception of velocity has been refined to upgrade it from a 3 component velocity to a 4 component velocity, we must do so for momentum as well. So, this is the 4 component velocity vector eta. The momentum, the 3 momentum, the usual 3 dimensional momentum, the Euclidean, the momentum in the Euclidean space that we normally talk about, is mass times velocity, but now this must go over to the 4 momentum, of which m times eta will give you 3 of those 4 components, and the 4th component turns out to be gamma mc, which is connected to the energy. So, the energy is like the 4th component of the momentum. So, in the special theory of relativity, energy gets introduced as the 4th component of momentum. In fact, the exact correspondence is here, that E over c is this gamma mc, which is the 4th component of momentum, the remaining 3 components being gamma times mass times velocity, which is gamma times this 3 momentum. Okay. Now, the reason this works is because if you construct the invariant quantity out of this, the quadratic quantity out of this, which is P0 P0 plus P1 P1 plus P2 P2 plus P3 P3, right, just like we constructed the invariant from the velocity, from the 4 velocity we construct the invariant from the momentum, from the 4 momentum. What we get is E square over c square minus P dot P. This is what we get. And this is manifestly invariant, because you get it equal to m square c square, where m is the rest mass, which is again it does not change from one frame of reference to another. Okay. Here again I would like to alert you to the fact that we introduce only one mass, which is the rest mass. Okay. Some older books also talk about a relativistic mass. You already see the energy mass equivalence in this relation, because if you multiply both sides by c, you get E equal to gamma times mc square, and these two relations over here give you E square equal to P square c square plus m square c to the 4th, right. So, this relation that you see in this block is the energy mass equivalence, which is mc square. If the 3 velocity is different, then the only component that will contribute is the rest mass, and then the rest mass will give you this energy, and there is no point in introducing a relativistic mass, because if energy and mass are equivalent, why do you need to introduce 2 quantities when they are connected? So, there is only one mass, that you talk about, which is the rest mass. And this energy is gamma mc square. E equal to mc square is best written as E equal to gamma mc square. There is a gamma factor which is sitting there. And if you look at this equation, you can ask yourself, what would this be for a particle which is travelling at the speed of light? What if V itself is equal to the speed of light? So, put V equal to c here. So, this becomes c square by c square, which is 1. 1 minus 1 gives you a 0 in the denominator, and the whole quantity blows up, it becomes infinite. Okay. But if the numerator also goes to 0, then you get 0 over 0, which is indeterminate, and maybe it makes sense. Okay. So, for particles which are travelling at the speed of light, which is a photon, the rest mass must be 0. Okay. So, for a photon, the V is equal to c, and then over here the rest mass being 0, this quantity vanishes, m square c to the 4th, and the energy becomes equal to Pc for a photon, the rest mass being 0. And the most famous equation in physics is perhaps F equal to ma or E equal to mc square, one of these two. F equal to ma is of course correct in the Newtonian limit, in the Galilean limit. E equal to mc square must be correctly written as E equal to gamma mc square, because you need to introduce only one new quantity, the two being energy and mass being equivalent. So, there is a energy mass equivalence. But the equation which I like most is this E equal to Pc, because it associates energy with my initials. So, we have the mass energy equivalence, which comes as an upshot of the special theory of relativity. But then there are other questions which remain. What is gravity? And this is something which we learned from Newton, that it is the force between two masses, and there is this g m1 m2 by r square. But let us think about it in terms of an example that we have discussed earlier. We discussed this example, if you remember, in the context of how a liquid in a beaker will look if this beaker is kept on a desk in the laboratory as it is over here, or if we are observing it in a satellite which is in a state of free fall. Okay. If this object, if we are all together in a satellite in a state of free fall orbiting the earth, how will this liquid look? And we agreed that since everything is in a state of free fall, it is not like zero gravity in the sense that gravity is not present, but it is with an effective zero gravity state. This is what we discussed, if you remember, when we discussed the accelerated frames of references. And in the absence of this any effective gravity, the liquid will take shape which is not determined by gravity, because gravity is missing in this state of free fall. We all agree that it is gravity which is making this water sit at the bottom of this bottle and not flying up within the bottle. Okay. In a state of free fall, this does not have to happen. So, the liquid inside this bottle will take a shape inside the bottle when the bottle is in a state of free fall, depending on whether the cohesive forces of the liquid molecules are stronger, or the adhesive forces of, which is the force of attraction between the liquid molecule and the molecules of the beaker, if those are stronger, it could actually stick to the beaker from inside. If the adhesive forces are stronger, leaving a cavity inside, and if the cohesive forces are stronger, it could form some sort of a globule just being suspended there. It does not have to sit at the bottom. The reason it is sitting at the bottom is because of the gravity it experiences over here, but that is not going to happen in the free space, in a state of free fall. Okay. So, we consider this liquid in a state of free fall, and it is no longer sitting at the bottom. It does not have to. Why will it? It is in a state of free fall, and the container itself is falling as freely as the liquid itself. Here the container is not falling, the container is held by this table. Okay? So, it is not in a state of free fall. So, this liquid will be suspended somewhere in the middle, forming a globule, and now if you to this beaker you fire rockets from the bottom of the beaker. Are we all together? Now, what is going to happen? The rocket is now going to get accelerated, the beaker is getting accelerated, and the liquid will gently come and settle down at the base, just as it would if it were in a gravitational field. On the other hand, so this is what will happen, right. On the other hand, if you fire the rockets sideways, why not? So, instead of firing it like this, you fire it like this, then the liquid will settle over here. So, you start seeing the connections between gravity and accelerations and geometry. Okay, you begin to see these connections, and these are fundamental to the general theory of relativity. This is what Einstein proposed in 1915, toward the end of 1915, almost 10 years after the special theory of relativity. And what he argued is that it is the curvature of space-time continuum which reproduces the effect which we normally attribute to gravitational attraction, because the two situations are completely similar. Now, the space-time curvature itself is determined by what? It is determined by matter. It is the presence of matter which determines the curvature of space and time. Now, all this belongs to the general theory of relativity. I am not going to go into those details, but these are very fascinating ideas, that what the presence of a mass does to space time. Now, space does not exist by itself, time does not exist by itself. What exists is the 4-dimensional Minkowski world, the space time continuum, which has got a certain curvature, and what gives it the curvature that it has is the presence of matter, and this is what generates gravitational attraction. And you can see the idea, this idea was in fact tested just a few years after Einstein proposed it in 1915 in experiments which were done by Eddington, because what this idea suggests is that the presence of mass, the presence of matter will change the curvature of space time, and if the curvature of space time is changed, then it will make the objects swing, so that it goes along a certain path. So, if this is to happen, then how can you test it? How can you test this prediction that the space time curvature is changed by the presence of a mass, and if you want to see noticeable effects, you really want to look at big events involving big masses. You can't do it in the laboratory with 1 or 10 kilograms of mass. You need huge mass to do this. So, Eddington proposed an experiment that if you look at effects which are generated by the presence of a mass as large as the sun, the sun has got a huge mass, and then the mass of the sun must influence the space time curvature in the vicinity of the sun, and it must make things going past it bend. So, light coming from behind the sun must get bent, and we should be able to see this deflection. So, now you have to look at light rays which are coming from behind the sun in the vicinity of sun. How do you see that? The sun is so bright, any light coming from anywhere else is coming from some other star, which is so much weaker compared to the light that you get from the sun, that you can't really do this experiment easily, right. So, what Eddington proposed, that if you do this experiment during a total eclipse, when the sun is completely eclipsed, so that the light from the sun itself does not reach you, and you can then, because of the reduced sun intensity, see the light which is coming from behind the sun, and then ask yourself, did you notice any deflection? And if you did, and if this deflection turns out to be exactly what is predicted by Einstein's general theory of relativity, you can get a quantitative estimate from what are known as Einstein's field equations, then you can conclude that Einstein's theory is correct. Otherwise, how can you get an experimental proof? So, this was the experiment which was proposed by Eddington. Fortunately, there was a total eclipse, and at that time of the year when the eclipse took place, which was on 29th of May 1919, what would be behind the sun would be light coming from Hades, which is a cluster of bright stars. And if you know, if you are familiar with the night sky, this is a picture of the night sky. Can you recognize what is what? Is this part of the sky familiar to you? Let me give you a hint. You have got the constellation Orion over here, Sirius star, or this is called as Vyad. This is somewhere over here. You have got the Orion. Okay, do you recognize it? Are you familiar with the night sky? So, I hope you can at least identify the Mruga Nakshatra, and then can you recognize the Taurus? Aldebaran, which is the brightest star in Taurus, and then over here you have the Pleiades, and this is the region of the Rohini Nakshatra or the Hades, and this is about 152 light years away, and the sun would be in front of this, and light from the Hades would go past sun and reach the earth during the period of the total eclipse, and what you would need to do is to measure the deflection of light. And this experiment was reported by Dyson, Eddington and Davidson in a paper called A Determination of the Deflection of Light by Sun's Gravitational Field from Observations Made at the Total Eclipse on May 29th, 1919. In a paper that was published in the Philosophical Transactions of the Royal Society of London. And Well, the deflection is to be expected even on the basis of special theory of relativity. Why not? Because we have already seen a mass energy equivalence. So, if energy, electromagnetic energy is going past the sun, there is a certain mass associated with it, even according to the special theory of relativity. But the deflection predicted by the special theory of relativity is not the same as the deflection predicted by the general theory of relativity. The general theory of relativity predicted a deflection which is almost twice as much as the deflection predicted by the special theory of relativity. So, Eddington recognized the fact that this would be measurable, this difference will be measurable, and if it turns out to be twice as much as is predicted by the special theory of relativity, then Einstein's general theory of relativity must be correct. So, that was the hope with which this experiment was carried out, and by Arthur Eddington. This is the path of the total solar eclipse on that day, which is in May 1919. It went from this place in South America, and it went past this town of Sobral in Brazil, which is where the experiment was carried out. The path of the solar eclipse, the totality, went even across the Atlantic Ocean. So, a second experiment was carried out on a ship in the Atlantic, and what you were to expect is that light from here, this place, if it is coming like this to the earth, it would get bent and come along this line. From the earth it would appear as if it has not come from here, but from here. So, that would be the apparent position of the source, and if that apparent position of the source is not the same that you are aware of from your measurements on other days outside the eclipse, right, then from comparison you can tell if the deflection did take place and was that deflection twice as much as is predicted by the special theory of relativity. Now, the story of this experiment is a very fascinating one. I will not go through the history of that, but I hope that some of you will read it and enjoy it. Eddington carried out this experiment and the conclusions were positive, and the general theory of relativity was verified. It is in fact a marvelous experiment that was carried out. This could be done because the eclipse was reasonably long lived. It was almost like 7 minutes, which is almost the same interval that we had recently in January, right, Jobin, when we had it at Trivandrum. We had a totality and partial eclipse in Chennai, and in Trivandrum there was a totality for almost 7 minutes. So, I do not know if this experiment was repeated during the recent total eclipse, if any laboratory did it. I would like to hope that somebody did it, and if nobody did, I think we missed a great opportunity, because totality does not last too long. In this case it lasted like 7 minutes, and the Trivandrum eclipse earlier this year did last for like 7 minutes or thereabout, and the general theory of relativity was established. I also mentioned that there are other consequences of the special theory of relativity, not just length contraction and time dilation, there are other things. And again, I will not go into details, but I will assume that you have heard about atomic wave functions, you have heard of quantum mechanics. You know that electron states are described by spin orbitals. We talk about the spin and the orbital, but in quantum mechanics there is really nothing like an orbit and there is nothing like a spin. So, these models are wrong, these are misleading. A spin is in fact an intrinsic angular momentum which is defined by certain commutation properties, and of course, I am not going to get into quantum mechanics to discuss this. What I want to point out is that there is an intrinsic angular momentum which elementary particles have, and these particles then turn out to be either fermions or bosons. And the origin of this electron spin comes from quantum mechanics, but not from Schrodinger's quantum mechanics. Schrodinger's quantum mechanics is not Lorentz invariant. It makes use of space and time and so on, right. It makes uses, it employs potential in which as a function of distance, and the distance parameter, the position that goes into the Schrodinger equation, is the Euclidean distance, the non-relativistic distance. So, that is really not relativistic, and this was then, again this is not going to be discussion on the formulation of relativistic quantum mechanics, which is a big subject by itself, needs a full course by itself. But when you put the special theory of relativity and quantum mechanics together, you get the Dirac equation for the electron, and what comes out of it neatly from the Dirac equation is the electron spin. So, electron spin has got no place in non-relativistic mechanics except in an ad hoc manner. You can always make an assumption, an ad hoc assumption, but from the point of view of relativistic quantum mechanics, it comes out neatly, it comes out nicely as a natural consequence. So, the electron spin is a natural consequence not just of quantum mechanics, but also of the special theory of relativity. It does not come from quantum mechanics alone. It does not come from the special theory of relativity alone either, but it comes from the special theory of relativity, without which it has got no place. So, amongst the several consequences which come as a package of the special theory of relativity, you must include not only length contraction and time dilation, but also quantum properties like electron spin and so on. And it should now become clear as to why physicists, chemists, material scientists, engineers, everybody must be somewhat familiar with the special theory of relativity. This is how a mass affects the curvature of the space time continuum around it. Okay? This is suggestive. We are not going to get, will not get into the Einstein field equations or anything and do this in any detail, but you get an idea. What you see is that the presence of matter changes the curvature of space time continuum around it, and then if you have an object, another mass which is in the vicinity, then it will go along this path and get attracted toward this mass. Now, you understand gravity. Why two masses attract each other? Because they find themselves in a space time continuum with such a curvature which sort of encourages their acceleration toward each other. So, what was only postulated by Newton gets explained in this mechanism through the curvature of the space time, and what imparts this curvature to the space time is the presence of matter, is the presence of mass. So, all these are consequences of the general theory of relativity. We talked about monkeys talking to each other on the cell phones. Every monkey does that. And I pointed out that this has something to do with the relativity theory, and it has to do not just with the special theory of relativity, but also with the general theory of relativity, because the cell phones work because of this global positional system, and you have got these 24 odd satellites which are communicating with the receivers, okay, and these receivers are in your pockets, and they are in the cell phones or in any GPS instrument, any navigation instrument. It could be a GPS map in your car or whatever. It tells you how to find your way when you are driving on a highway and you do not know how to get to your destination. So, these satellites will tell you, they will navigate you through this, and all this works because the information sent by the satellite is correctly received by the receiver in your pocket, and it should get to your pocket, pass through a certain distance over a certain amount of time, and if this distance and time is not calculated correctly, there will be errors. And distance and time are not absolute quantities, they must be determined with reference to the state of motion of the receiver, the satellite and everything else. So, to do this correctly, you must employ special theory of relativity. Otherwise, the errors are quite large. The location, the message that you get on your cell phone when your friend calls you, it lands on your cell phone, could easily land if these errors, the way these errors accumulate, that if you did not include relativistic effects, they could land like 10 kilometers away, and your girlfriend is calling you and the message goes into your father's phone. That is terrible, right. So, these things need to be calculated correctly, and you must include the special theory of relativity, so that time and distance is correctly estimated. Not only that, the receivers are in your pockets, they are on the surface of the earth. The satellites are like 20,000 kilometers away. So, look at the curvature of space time. This curvature is bent most closest to the mass and least as you go farther away, and this is not due to special theory of relativity, this is due to the general theory of relativity. And 20,000 kilometers is a distance that is large enough for this factor to influence the time intervals, and both special theory of relativity and general theory of relativity must be properly accounted for. Otherwise, the errors are quite large. I believe they turn out to be something like 7 microseconds per day if you ignored special theory of relativity, and something like 45 microseconds per day if you ignore general theory of relativity, but in the opposite direction. So, the net error turns out to be like 36, 37 microseconds per day or something like that, means I forget the numbers. And it is for this reason that a comfortable acquaintance with the special theory of relativity at least is what I strongly encourage at the undergraduate level, and I hope that we at least have some sort of an introduction to it. Finally, we must ask ourselves, we have used Newtonian mechanics, Lagrangian mechanics, Hamiltonian mechanics, Galilean relativity with a good amount of success, and now we are saying that okay, space is does not have an identity of itself, this which is disjoint from time. So, it is not that this is absurd. Yes, it is wrong because it takes only a part of the story, but it is not totally absurd because the speed of light is not infinite, but it is very large. So, in the limit that V over C goes to, when V over C is much smaller than 1, okay, when V goes to 0 for example, it works all right. Of course, Newtonian and Lagrangian mechanics has to be corrected not only for relativity, but also for quantum mechanics, and the reason classical mechanics works is also because the Planck's constant of action, what I have written here is h over 2 pi. This is also a small number, and in the limit that h cross goes to 0, you will get classical mechanics in the limiting case. Not always, but again these are very subtle issues, I will not go into that at this point. But by and large, the v tending to 0, the h tending to 0 is the limit in which Galilean relativity works. But with the special theory of relativity, we are able to include in our range of applications also the electrodynamic phenomena, which we have already discovered must have a relativistic basis. So with that we conclude this discussion. I will just point out that Einstein's contributions go well beyond relativity. I mentioned his contribution to the Brownian motion, to the interpretation of the photoelectric effect. It just goes on and on and on and on. And then together with Satyendranath Bose, the Bose-Einstein statistics, which is a very exciting subject, especially in the context of laser cooling and Bose-Einstein condensation and other things that scientists are working with. So these are, Einstein has made huge contributions to physics in very many disciplines, and we will conclude this discussion on unit 6 with one quote from Albert Einstein, that if an idea is not absurd, if it does not appear to be absurd at first, then there is no hope for it, because you see that this really looks like an absurd idea, the special theory of relativity, that the speed of light is the same in every inertial frame of reference. I mean, how can that be true? Okay, we talked about intuition, then counter intuition, then educated intuition, and then we came to grips with it. All that is fine, but when this idea was introduced, it was absurd. It looked absurd. But our experience is that there is no guarantee that there is hope for every absurd idea. So thank you very much. If there are some questions, I will be happy to take. Otherwise, goodbye. And then we will have the next unit, which is unit number 7, in which we will deal with potentials, fields, and gradients. So that will be for the next unit. If there is any question, I will be happy to take. Let me just say one thing over here, that I have met students who feel shocked when they see that one of the siblings has aged more than the other. Now this shock is not called for, because this shock comes after the student has accepted that the speed of light is the same in all inertial frames of references and the idea of time dilation is accepted. So please do not die twice of the same shock. Okay? Once you accept that the speed of light is the same in all inertial frames of reference, then any consequence which is a natural outcome of this consequence, which comes simply by putting numbers in this square root of 1 minus beta square, should not shock you. If it shocks you again, it will be dying twice by the same shock. So do not let that happen. So good luck, and we will meet for the unit 7.